All right, so lecture number 20, singleton classes. So we're going to talk about singletons first, even though you probably may know about them already, and C++ visual profiling. So this lecture is not a required lecture for your project, and I know half of you probably turned it off, but if you are actually interested in becoming good software engineers, good game developers, good programmers in general, then you should care a lot about a topic like this. And this is one of those lectures, in my opinion, probably overall, when it comes to all of your programming career, this may be one of, if not the most important lecture of like this term, in terms of actually helping you write performant software. All right, so before we get into the visual profiling, let's talk about singletons. So if you know what a singleton is already, that's okay. This won't take too long to explain, but maybe you haven't seen them in C++ before. So a singleton is a programming pattern. Excuse me, one second. Coughing today. All right, so a singleton is a programming pattern, meaning it's a type of thing. It's not a data structure. It's a way of programming a class, for example. So it's typically implemented with some sort of object-oriented programming. So in a programming language that uses OOP, typically we implement singletons as an object. And there is a specific pattern of implementing that object. And the whole point of a singleton is that a singleton class ensures that only one instance of that class can be created. Okay, so whenever you might want some sort of global functionality, so for example, if you have a logger, so if we have a logger that's just printing out to a log file, some sort of blackboard, I'll tell you what a blackboard is in a little bit. Whenever you have some sort of global functionality where you have a class that I'm sure that I only ever want one of them to be instantiated, then you should use a singleton. And the implementation of a singleton depends on the language. And there will be people out there that will say that if you're using a singleton, then you're doing it wrong. Or people sort of view singletons as like a hacky way to implement something. I really don't believe that to be true. And, you know, I'm not a professional industry game developer who's been doing this for 40 years. But if I can find an argument that tells me why you should never use singletons, I still haven't found a good one. In fact, I think they're pretty useful for some things, and I'll show you a couple of instances of that in this class. Now, singletons are not the only way to implement this functionality, but in my opinion, they are a safe way to implement global functionality, and so why wouldn't you use them? All right, so C++ makes implementing singletons very, very easy. We can make use of a static variable and a static function to ensure that only one instance of a class can be created. We will also make the constructor of that class private so that no other code could accidentally instantiate it. So let's see what that looks like. Here's an example C++ singleton class. Now, when we implement a singleton, let's say, for example, we have a logger, we would say class logger. There is no class singleton that we inherit from or anything like that. I'm just showing you that this name singleton here could be replaced with any class that you want to be making a singleton. So the first thing that we do is we make our class constructor a private constructor. That way, nobody outside of this class can actually construct this class. Next, we have a singleton function, and that is a static function. And if you're not aware, what static means when it comes before a class function means that this function is not tied to any instance of this class. It is just a function that you can call. Okay, so you can call this function that is not on an instance of a class, and if you have non-static functions, it means that you have to have an actual object instance in order to call it on. So this static function singleton, the static function returns a reference to a singleton, and the function is called instance. And what we do in here is we set up a static singleton instance and this is only ever run once. So we talked about this before, how if you instantiate a singleton variable, then that line of code is only run once. So the very first time that you call the singleton instance function, it sets up the static instance, and then it returns it. And, well, it returns the reference to this instance. And after that, the only thing every other time, so the second, third, fourth, up to the whatever time that you call the instance function, this line of code is skipped, and it just returns that instance that we already have set up. And so we are guaranteed that this instance is created the first time we call this function, and that no other instance of this class will ever be created, unless we do some crazy hacking somehow. All right, and then let's say we have some other non-static function on the instance class, and then the way we would call functions on that single instance of this class is that anywhere outside that includes singleton.h, we would be able to say singleton : because this is the class namespace, instance that gives us the instance, and then we can say .do thing, right? So let's look at an actual example that we may actually want to implement. So let's say that we have a logger, right? And the whole point of this logger class is that we want to be able to log things to a single file. So our whole program, no matter where we are, we would like to say, okay, let's log some important data, like we connected to the server, or the player jumped, or the player did this action, or we had some lag frames here, or something like that. So we want all of that to be going to the same log file, ideally. So what we do is we're going to create a singleton class called logger. And in the private member variables, we're going to create an output file stream. And that output file stream, we're going to open up, say, log.txt, right? Makes sense? And then our constructor for this class is going to be private. And then in our public section, we're going to have our instance function, which is static and returns a reference to the only instance of this logger class, and then does the same thing, where we say static logger instance, and then return instance. Then we have a function called log, and that log function takes in a const string reference, and what it does is it prints that to the log. Okay, so it adds it to the end of the log file. And so anywhere in our program where we want to log something out to this file, we would just call logger : instance.log, and then the function. Okay, so the only really annoying thing about this is that it's kind of verbose, right? So you could say that, okay, logger : instance.log, that's like getting into Java levels of verbose, right? Like system.out.println. So what we can do if we want, but in general we probably shouldn't do this, is we can do something cool to remove this instance call. So if you get annoyed by that instance call, you can do a little bit of trickery to eliminate it, but just realize that it might be a little tedious if you have to do this with all your functions. But let's say for the specific case of this logger, we actually want to be able to just say logger log instead of this instance call. So how would we do that? Well, what we would do is we still have our public log function here, okay? However, we now have a private function called log implementation, which actually does the logging, right? And I just removed const here because I had to fit it on one line, otherwise it wouldn't fit. So this private function actually does the logging, right? This is the thing that actually puts it out. But now we have a static function on the logger class called log, which calls instance, and then on that instance calls the log implementation. And so see how this sort of pattern goes? You can make a private function that actually does the thing, and then you can make a public function which calls instance. And so now you can just say logger, log, hello there. All right, so that's how you would do that if you want to. I'm not saying that's good or bad practice. I just wanted to show you a little fun code snippet there. All right, so that's what a singleton class is. And, you know, I'm telling you that because we'll come back to this. This is a bit of foreshadowing for the rest of the lecture. I mentioned blackboards previously in the class, and now blackboards aren't something that we are going to be implementing in our game. I don't think our games are necessarily big enough to require a blackboard. But game developer articles, if you read a bunch of game dev articles or game dev books, they often refer to a data structure known as a blackboard. And typically, what this blackboard is some sort of global data storage or data management, right? And so a blackboard could be implemented as a singleton. And the idea here is that keeping all of your global data, so for example, it's keeping it in this blackboard singleton is probably cleaner and safer than just using global variables, right? It might be a little bit more code, but maybe it's safer than doing that. So for example, some games may require some global knowledge. Let's say, I don't know, what level you're on is really important to a bunch of different parts of the game engine for some reason. So you could store what level I'm on in the blackboard, for example. And now any of your horizontal systems in your game engine are going to be able to know what level you're on or how many lives you have left or something like that. Now, you may argue that keeping this global type of data is bad practice. Whatever, that's fine. I'm not teaching what blackboards are and how they're used in this course. I'm just mentioning it to you that this could be implemented as another use case for a singleton in game design or game programming. Now that we know what a singleton is, let's talk about code profiling. All right, so profiling code. What is profiling code? Why do you need it? Why is it important? So profiling code involves timing specific functionality in order to see how long different functions or different methods take to run. So for example, we could just run our program and time how long the program takes. And that's not necessarily, I mean, it's a form of profiling. It's really, really basic form of profiling, just saying, okay, it took 10 seconds to run. But profiling really involves, that would be timing code if you just time our program, see how long it takes to run. But the idea of profiling is to say, for example, how long specific things within our code are taking to run. And so, for example, Visual Studio has profiling tools built right in. And that's really cool. You can actually just run a profiler in Visual Studio and it will start to profile your code and see maybe which systems are taking longer, etc. However, before you start profiling, before we actually give a demo of that, there are several types of code profilers, and let's explain those before we get into them. So first are event-based profilers. And event-based profilers typically are used when a language or API has built-in support for them. So some language or API may have built-in events which trigger profile data collection. And that means that they provide hooks to events such as function calls, memory allocation, class construction, entering or leaving threads, etc. And so the language has support for this. And they rely on specific functionality implemented in the language or the API that's being used. And of all the three different types of profiler that we're going to be talking about, these sort of have the lowest resolution, if you will. So event-based profilers kind of look like this. Let's say we have the Java virtual machine. And so JVMPI is this like multi-processor or parallel library that you can use for Java. It has events built into it that let you do some profiling. And so you have some profiler agent, you have a front end, and what happens is this agent sort of runs in the background, listens for events, and then is able to profile your code even in real time sometimes. And so this is an event-based profiler. I'm not going to talk too much about event-based profilers because we're not going to be using them in our demo today because they just exist and you can use them. And that's not very fun. We want to implement things ourselves, right? So we're going to implement our own profiler, not just use one that exists. Probably one of the most popular forms of profiling and the easiest form to use in C++ would be a statistical profiler. And what a statistical profiler does is that it collects profile data using sampling. And so the call stack of a program is probed at regular times using operating system interrupts. And so what happens in a statistical profiler is that you run your code and then some other program just asks your program, hey, what are you doing? 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 Like, what function are you in? What's the call stack look like? Right? What line of code are you on? Something like that. And so it just asks every so often, might be fractions of a millisecond, might be every second. And then the idea here is that the statistics about those samples are displayed to the user for interpretation. And so, for example, if 30% of the samples were collected, shows that the program is in the render function, then you know that approximately 30% of the running time of your code is the rendering, right? Now, it's not exact, but if you collect enough samples, then it averages out to be pretty close to exact. And so the results, like I said, are not exact. They are sample-based, but there's very little overhead in doing this, and you can collect so much data that the results are actually quite good. So here's what a sampling profiler looks like. Is that you're running some code, I'm here, I'm calling these functions, and so you are just polling. Let's say your program runs for 5 seconds here, and then, so 5 seconds, it's going to sample once per second, for example. Now that wouldn't be a very good profile or sample rate. You want to do this like thousands of times per second. But if this ran for 5 seconds and we took 5 samples, 1 per second, then you can say, okay, what does that mean? Right? So for example, I was in the order function one of those times. I was in the lookup function one of those times. So we can see how often we were in a particular function divided by the amount of functions the amount of times that we polled, and we can draw some conclusions about that, about which functions took the longest or where we may want to spend some time optimizing. The third type of profiler that we will talk about is called an instrumentation profiler. So in an instrumentation profiler, it kind of involves the most amount of work, but it also produces the most exact results. So in an instrumentation profiler, instructions are actually added to the program to collect and output the desired type of profiling data. So it could be done manually, it could be done by the language, it could be done by the profiler, by the, what's the other word? Oh my God. My mind is completely blank right now. By the IDE. It could be done by the IDE. A lot of different things could do this. So this profiling data will be exact. It will be exact. However, it's kind of like Schrodinger, right? So Schrodinger's cat, where in order to instrument, you actually affect the running time of the program. Because if you insert instructions, those instructions take time, and so it can change the running time of the program. So ideally, starting and stopping the timers, collating data, and outputting that data to a file, that can actually take some amount of time, right? And so this allows for very, very fine control over what we want to profile, but it is going to add some amount of running time to the program. So for example, if our program took 10 seconds to run, if we add this instrumentation profiling to see, okay, where were those 10 seconds being spent, now maybe our program takes 10.1 seconds. Now, generally, it's not going to have that much of an impact. It's going to be pretty negligible, but it will make the program take longer to run. It just will, right? Because adding instructions makes it run longer. So what we're going to do now is we are going to implement a manual instrumentation timer for C++, and we're going to be able to visualize the output of that instrumentation profiler. And that's going to be, I don't know, this is going to blow your mind, hopefully, because it blew my mind the first time I saw it. All right, so this is what it's going to look like. If we want to know how often and how long some function took to run. Like, for example, we want to know that this function on average took 3 milliseconds to run, and here's where it ran in our code. We can just insert this thing that says profile function. And that will be this manual instrumentation code insertion. And then you write your code as normal. But all you have to do, any function that you want to instrument, that you want to profile, you would just put this profile function call at the top of it. So what we could do as well is we can profile functions and we can profile scope. So if we want to profile this entire function, we would just say this at the top of the function. If we want to profile a scope, we could give it a name and we could profile an actual loop iteration. So this system of what this actually does, how it works, that's what we're going to be showing for the rest of the lecture. But first, what I want to do is I want to actually show the Visual Studio Profiler. And so the Visual Studio Profiler, we can hop over to Visual Studio, and here we have the, here we have the source code for assignment 3. This is the solution. So if I run the solution for assignment 3, here we go. So I am jumping around inside assignment 3. This is assignment 3, right? All right, so what I'm going to do is I have to do no extra work in Visual Studio. I can come up to here to debug, and I can go to Performance Profiler. Now, I know this font is a little bit small. Apologies for that. I couldn't find how to make the menu font bigger. I know it's there, but I remembered too late in the lecture. So it says Performance Profiler Alt F2. So I can click this. Then what I'm going to do is click CPU usage. Okay, so I'm going to click CPU usage, and then I'm going to go click Start. Now, I'm not going to click Instrumentation. If you don't click Instrumentation, then this will be a sampling-based profiler. So if I click Start, it'll compile and run my program as normal, except it's collecting diagnostics in the background. So what we're going to do is we're just going to run around. We're going to run around for, let's say, 10 or 20 seconds, right? We're collecting samples in the background. So here I'm killing some stuff. I'm running around. Okay, I'm shooting. You generally, when you're collecting samples, you want to have a nice like sample of all the things you can do in the game. Look, I can drag stuff around. That's the last lecture. I kept that in here for this lecture. So there we go. I've collected enough samples. Now I stop my program, and Microsoft is now collecting all the diagnostics from that running of the program, and here we go. So it has finished, and this is the screen that you are presented with. Okay, and so there's a number of different ways that you can view the profiling data. Why won't this move down? Okay, it won't move down. Up here, this is like the highest level view where it's sort of, this is the CPU usage. Now, my computer has like 16 cores or something like that, so this isn't really all that useful to us because it's saying like total CPU usage. But down here, we're going to click on main. So if I click on main, let me zoom back out of this. What will show up? I'm going to close the output window. All right. So on top, we have this sort of table of what the sampler data collected. And on bottom, we have code down here that we can see. So there's a bunch of stuff that happened in our program that wasn't our code. There's a lot of operating system stuff. There's a whole bunch of SFML stuff. It turns out that the vast majority of our code is actually spent in SFML on that waiting to render stuff. So if I go into main, now I can see, okay, 31% of my program was spent in main. All right. Now, there's some other kernel stuff happening. This is it's actually kind of bad to use sample-based profilers when you're using an external API like SFML, because most of our stuff that's happening, remember how we set a maximum frame limit of 60 frames per second? Well, when we do that, it's because we want the game to run at 60 FPS, but that means that the vast majority of our program is actually spent waiting for the next frame to draw. So here, in our rendering system, you can see that like the majority of the code that was in our program was spent in SFML graphics doing the rendering calls, okay? But outside of that, what did our game engine actually spend its time in? Well, you can see here that it was called in init. And look, oh, assets load from file. Load from file took about 1.44% of the running of our program. Look, game user input took 3% of the running of the game of the program. Down here, we've got a scene play update. Oh, look at that. The most expensive thing in our update code was the collision function. So inside the collision, oh, look, it's the physics get overlap function. And so of our functions that don't have to do with rendering, it was actually like our collision system that's taking up the most of our time, right? And so our we can see here that inside update, our animation system took almost no time in comparison to collisions. Entity manager update was barely profiled at all. But you can see here that there's really not that many samples collected. And so I would have to run my game for a while longer than this in order to collect like really accurate data about what's going on. And all this SFML stuff, like the game spent so much time in SFML waiting to redraw the frame that my sampling-based profiler was not really working as accurately as it could have. But that is a sample-based profiler. So let's close this. We will not save the diagnostics. And let me go up here, and now I am going to go to Debug, Performance Profiler. This time, I'm going to, oh, I can't do instrumentation because it's not a managed language, okay? So the instrumentation part, I could also do GPU usage. I'm not going to go into that here. We could do memory usage to see how much memory we were taking, but there are some nice tools. But in a managed program, which we are not doing because we're just doing a console raw C++ program, we could do instrumentation, but we can't with our particular assignment. So let's go back and we will look at how we can do our own version of an instrumentation-based profiler. So that was the demo. Now we are going into our C++-based profiler. However, before we write a profiler, we need a timer, right? So we need a timer written in C++. So let's write a timer in C++. So the basic logic, whenever you time some code, is that you're going to record the starting time somewhere, then you're going to record the finish time somewhere, right? So you record the starting time, then you run your code, then you record the finish time. And then the amount of time your code spent is elapsed, and that's equal to the finish time minus the starting time. That is how you record and time data. And so standard chrono is in the modern versions, I think, since C++ 17, and that gives us pretty accurate timing tools for C++. So we have standard chrono high resolution clock now, and that will give us a timing based thing. Okay, 1 second. Someone just gave me a tip. Let's see if this works. So if I unchecked CPU usage, oh, we can do instrumentation. Excellent. Let me start that up. It is going to, let me see here. Project, click OK. It has to recompile it with instrumentation enabled. So let's see what this looks like. Here we go. Thank you for giving me that tip. So here we're running around. I'm going to spend a couple more seconds running around. Break some stuff. All right. Now we're going to close the program and see what gets output now. Okay, perfect. So this is the instrumentation-based timer. And we're going to click on main. And here we can see, okay, excellent. So if we go into summary view, no, I want functions view. Here we go. So this will show me all of the functions in the program. And I want elapsed inclusive time to show me like where everything spent all of its time sort of hierarchically. So I can see that, all right, my main function is where 99% of my program was spent. I can't include the font size of this. I hope you can read this. So 98% of my program was spent in main, and of that 98.6%, 91.75% was spent inside SFML's display function, just waiting for the program to display again. So that's unfortunate. But at least instrumentation tells us these exact numbers. So game engine init, that took the longest time in total of our inclusive running time. And inclusive running time, there's two types of running time. One is inclusive, one is exclusive. Inclusive means how long did it spend in this function and all of its child functions. Exclusive running time means how long did it just spend in this function only. Okay? So, for example, in game engine init, it spent 2.14% inclusive time in that function, but 0% exclusive time in that function. And that tells me that, okay, it was the functions that were called by that function that took all of the running time. If I look at my exclusive running time, I can see which functions actually took the most amount of time inside that function itself. And if I do that, well, actually, I want to see inclusive time for now. So inside update, actually, let's look at here. I can say caller and callee. I think this is what I can do. Functions. No, call tree. Here we go. Call tree. So this will hierarchically give me that same view. And I can see, okay, inside game engine init, it was, oh look, it was actually SFML creating the window that took most of the time. I would have assumed it was the reading from the file, but reading from the file actually took 1/6 of the amount of time that creating the window did. If I come down here, I can see my scene update, and yes, it was indeed my collision function. And you can see that my game ran for approximately 962 frames. So my collision function was called 962 times, and it took 0.43% of the running of the program, and inside the collision, it was my get overlap function. Holy crap! I called get overlap 150,000 times, right? So that's why it's really important to optimize the hell out of this get overlap function, because it took it was called 150,000 times. All right, so this is a cool way to see this data inside, to see this data. I could go in and say, okay, the destructor of assets took a while. Let's say our rendering function didn't take too long inclusively. Our update function, entity manager update, that's what I wanted to see. Okay, so 53 times we called remove dead entities, and that, so we can see, like, that took 0% of the running time in the program, so that's not our bottleneck, etc. So thank you to Alejandro for telling me that. I just had an option checked improperly. So let's get back to writing our own instrumenter. So what that program just did is what we are going to be creating now from scratch, and we're also going to be writing a visualizer for that. And of course, my cat is yelling to get out, so before we get started with this for the second time, let me just go let him out really quick. All right, so for the second time, C++ code timer, how would we write that? Well, we already talked about this a little bit. So the basic logic for timing the code is we record the starting time, we run our code, we record the finish time, and then we just subtract them to get the elapsed time. And C++ actually built into the library gives me tools for doing that at a high resolution. Like sub-millisecond resolution, so it's pretty good. So we're going to write a class, okay? So we're going to write a C++ timer class, because having to record manually the start and end times and doing all that math and stuff, that gets really, really cumbersome. And so we're going to be good object-oriented programming people, and we're going to make a little class for that. So our functionality that we are going to have in this C++ timer class is going to store the start time whenever we call the start function. We're going to be able to query how much time has passed since we called start with elapsed. And we are going to have the ability to start and stop the timer at will. And what this does, it is going to abstract away the standard chrono syntax, which is, as you will see, incredibly verbose. So standard chrono is great. It gives us a lot of functionality built right into C++, but it's pretty verbose. So we'll see exactly how verbose. So our timer class is going to include chrono. Okay, so that's the library. As you know, chrono means time. We're going to record the starting time and the end time, and we are going to have longs for this. So this is a 64-bit integer. And then the way we record time is with standard chrono time points. And this is on the standard chrono high resolution clock. And this is m underscore start time point. So STP, that is our starting time point. So when we construct our timer, inside the constructor, I am going to call the start function. And the start function is going to record our time point as now. Okay, so whenever we start our function, we start the timer. Or whenever we call our timer, by default, we start it right away. We could restart it again later if we want to, but it starts as soon as we construct the object. Now, we have start functionality implemented. Now we want the elapsed functionality to be implemented. And this is going to return the time elapsed in microseconds. So wow, okay, so it's a thousandth of a millisecond. So here, because the standard chrono gets so long, within this function, we are going to be using standard namespace standard chrono, just so I can fit this stuff on a single line. So here, I'm going to say auto end time point, and I say auto because I don't want to type standard chrono time point, standard chrono high resolution clock, so I just say auto. Auto is wonderful. So this is high resolution clock now, and I can not have to type standard chrono because we're using namespace standard chrono just for this function. So I record the end time point, then the starting integer, okay, so this is recorded in microseconds. I time point cast my starting time point to microseconds, and then I record the time since epoch.count. So this is verbose, I know, but once I have these two things and I have done this to both of them, I can take end minus start, and that is the elapsed time in microseconds. Okay? And you can see how this would get insanely annoying if you wanted to like actually do this everywhere. So we're just going to wrap this in a nice little function, which is called timer, or a class called timer. If we actually want to use the timer class somewhere in our code, then we would just do this. Well, here's our main function. We're going to create timer t. Now, timer t, this calls the constructor, and we may, and it's going to start ticking immediately. But maybe we wanted to do some other things before we actually start timing something. So after maybe we read from a file or something like that, we would call t.start, and that would reset the starting time, so the timer starts now. Then we would call some function or do some machine learning or run our game or whatever. And then we say auto elapsed equals t.elapsed. And so we record the amount of time that it took, and then we could print out the amount of time elapsed is this microseconds. All right, so that is how we write the timer class. This is a fully functional timer class that you can use in C++, and this is a fully functional use case of that timer class that will actually work. So that's fine. Now we have a timer, but you can see how doing this everywhere would be incredibly cumbersome, and all we'd have is a bunch of stuff printed out to the console. So what we want to do is create a visual profiler so that we don't have to read through console statements, we don't have to look at tables of values. I want to be able to visually see what the time is taking in my game, or where the time is being used in my game. And I just realized this lecture is going to go a little bit over time, so I apologize for that. But this is sort of not necessary for the course, but me just wanting to give you as much knowledge as possible because I really like this topic. So I want to give credit where credit is due. This lecture was inspired completely by this video by the Cherno YouTube channel, and it's called Visual Benchmarking in C++. And what the Cherno did was a very basic form of what we're going to be doing. My code is going to have some fixes and some quality of life improvements on top of his code, but it is essentially what he did in that lecture, but we are going into more detail. Okay, and so this code is an updated, simplified version. It is very, very simplified. Like his video was very, very good, but I question why he made some of the decisions that he did. And then there was some discussion about he uploaded his code to GitHub, and then some people made some comments, and we were discussing back and forth about it. And then this lecture is sort of the end result of that discussion. So just wanted to give that credit to where I got the inspiration for this lecture. So visual code profiling, what does that even mean? I've been talking about it. Humans are visual creatures. Staring at text output is very difficult to understand. What if we want to visually profile code? What if we could get something like this? Right? So this would be cool if we could actually see a visual breakdown. Oh, wow, like here's my collision code. Here's how long that takes in comparison to my rendering. And here's how long the drawing of my entities takes, or the drawing of the grid, or the user input system, or whatever, right? This is what we want. So we can actually see at a glance how long everything takes in relation to each other in our program. All right. Cool thing is, it turns out that Chrome, Google Chrome, the browser, has really nice visual tracing functionality built in. And so what you see here comes straight from Chrome. And initially, this was meant for website profiling, but you can input files in a very specific JSON format, and you can go to the format here. It's not super important because I've done all that for you. But if we can output our timing code with this specific format, Chrome can visualize it for us. So the cool thing is we do not need to write our own visualizer. Here's an example of the Chrome tracing JSON format. Each of our profile samples, or our instrumentation samples, well, they're not samples. Each of our outputs have to have this information. So it has a name, a category, it has a timestamp, a tracing clock timestamp in microseconds. It has a process ID, a thread ID, and then some optional arguments. But here's what it looks like in practice. Excuse me, I have to sneeze. I hate when a sneeze goes away and then you just look at an idiot. All right. So you have this trace events data structure in the JSON file, and you have a category called function, a duration, a name, and a timestamp of where it started, and that's it. So you have where it starts, how long it took, and a name. That's the important stuff. And down here, what you get is this duration was 2. So the function 1 took 2 million microseconds, or 2 seconds. Then function 2 started right after that one and took 1 million microseconds. So if we look down here, we see that function 1 took 2 seconds, and right after that, function 2 took 1 second. So our entire running of our program took 3 seconds. So this is a lot easier to look at than this. And the cool thing is that if we have another function start not after the previous function, but during the previous function, so if function 2 called function 3, for example, then it will visualize that for us. So let's do a really quick demo of this. So I have Chrome open here, and I have some profiling code that I have already generated. So here is Chrome tracing. Now there's this other thing called Perfetto, which is a more sort of professional version of this that I'm not going to go into because it's just a little bit nicer, but I want to show you, hey, everybody has Chrome. So here is a JSON file that I have already created, And this is the example that we just did. And so in here, in the profiler, I can drag this around, I can zoom in, I can zoom out, and you can see, oh look, this code took about 3 seconds to run, right? If I click on the function, down here you can see the starting time of this function was at 0 milliseconds. The wall duration was 2000 milliseconds, so that took two seconds to run. Then this one started just after 2 seconds and took 1 second to run. Now this is a pretty basic one, so let's pull in one that's actually from our game engine. And look at this. So this is pretty cool. Our game engine platformer init, you can see, oh look, loading the assets from file took half a second. And if I come into here and I zoom down, oh look, this is where I actually added some textures. So this texture was probably bigger than this texture, right? So you can see exactly where the file loading was. Here, I added some fonts. So these fonts took a little while. I wish I could sort of make this bigger, but Chrome tracing is not very good when you go to zoom in. Adding sounds took a while. So this sound took 78 milliseconds or 40 milliseconds to actually load from the file. If I scroll over here, you can see, oh wow, but this is when I was memory pooling. And so this memory pool took almost a second or half a second to set up. Then you can see in here, oh look, this is each of my game engine's on-frame calls. So my game engine on-frame, well, this is my gameplay on-frame, and you can see here all of my systems. So this is my movement system. That took less than a millisecond, or like it took 0.069 milliseconds. This is my mouse over system. Here I have the lifespan system, the collision system, okay. On update effects, rendering. So down here I can see, okay, here is my circle line collision. So this is a different engine. This is not your assignment 3. But I have circle line collisions. I have detect collisions. All sorts of stuff. But you can see here that, okay, now my rendering, the drawing of my entities took this long. The drawing of my grid and my walls and my text. I can see like exactly how long each frame took. And this frame, that is taking 16 milliseconds because it's 60 FPS. And I can see, oh wow, the logic for my game is taking way less than that 60 milliseconds. So I have all this time to spare, and all of this time right here is just spent waiting for SFML to draw that next frame. So isn't this cool? Like that you can visually profile your game like this? And so the thing that lets us do this, that actually outputs this data, is what we're going to be making for the rest of this lecture. Sorry, my phone just went off, so I'm going to turn that off. All right. So that's the demo, and that's how powerful visual profiling is. So visual profiling in C++. It seems like, you know, C++ is a bit of a manual language. You kind of got to do stuff yourself, right? So how do we transition from the timer class that we just created to outputting the JSON file to visualize that data in Chrome? Now, just keep in mind that this is not the only way to do this. It's just kind of an easy way to do it because we're using Chrome's visualizer, which is pretty nice. The timer class cannot output to the file itself because all the data needs to go into a single file, right? We need all of our data to go to this single JSON file. And so, if we only had a way to globally write to a single file somehow, right? Remember how I said there was foreshadowing? Singleton to the rescue. Singleton to the rescue. So here is a class that we're going to write. Here is the initial implementation of a profiler class. And this profiler class, it's going to have, just like our logger did before, it's going to have an output file stream, and that's going to be result.json. And our profiler is going to be singleton, so our header, or our constructor is going to be private. Whenever we construct this profiler class, we're going to write the JSON header inside the constructor because the JSON file needs a little bit of a header. Then we have our static instance that returns the profiler. This is the same as before, just makes it a singleton. And then we are going to have a function on the profiler class called writeProfile. And we're going to have this other thing, a struct, which holds some data called a profile result. And so we're going to have a profiler. We'll write another function. I'll show what this profile result is. It'll write the result to the JSON file. And then when the program stops, our profiler is going to be destructed. So singleton classes get destructed when our program stops. And then we write the footer of the JSON. Okay? So whenever the profiler is constructed, we write the header of the JSON. Whenever we have a result to write out to the file, that gets written out to the file. And then whenever the profiler gets destructed at the end of the running of our program, we write that out. We write out the footer of the JSON file, which completes it. Okay? And so the singleton will destruct when the program exits normally. And the main idea here is that when the timer stops, we write, we call profiler instance.writeProfile. Okay, so whenever our timer stops, we call this to write out the profile. And this profile result that gets written out to the JSON file is going to contain, because we need this information in order to visualize it, a name for the box in the visualization, a start time, an end time, and a thread ID. Now, we're not multi-threading anything, so our ID is just going to be 0, but the JSON output format does require a thread ID. So our timer elapsed function, what it used to be was this, right? So whenever we called elapsed, we would just calculate the start time, our start time was already calculated. We calculate the end time and we return mEnd minus mStart. So elapsed used to return the amount of time that had elapsed since I called start. But now what's going to happen instead is that we are going to have a profile timer stop function. We are going to start profiling, and then we were going to stop profiling. So our profile timer's stop function is going to have this result, right? It's going to store the start and end. And then, so the start is going to be calculated, the end is going to be calculated, and then when we stop, profiler instance.writeResult. So instead of returning the amount of time that it took, we are going to write the profile result to our JSON file. So here's an example usage of this profile timer, okay, if we want to use it in its rawest form. So inside our main, we would say profile timer T, and we'd say main, right, because this is a name that we want to give to that. Then maybe we do some other things. We're going to start the profiler, call some function, and then we would call t.stop. And when we call t.stop, it stops the timer and the profiler logs it, right? Because whenever we call stop, it logs it to our JSON file. So that's all we would have to do if we want to manually use this profile timer. But calling the profile timer, giving it a name, saying start, saying stop, it's still super inconvenient, right? It's better than manually using a timer. It's better than manually calling standard chrono, but still it's not at the level of convenience that we want. So convenience here is really key. Convenience and modularity. If we want to profile a lot of areas of code, then manually starting and stopping the timer each time will be super annoying, right? And it'll mess up our code. Imagine if every function that we wanted to profile had to have these 3 lines of code in specific points. Oh my God, that would be super annoying. So let's develop a way to time a block of code by typing 1 line of code, a single command, all right? So any block of code that has this code or this command at the top of it will automatically be profiled to the JSON timer. And so the first thing we're going to do is that we're going to make the profile timer stop and log in its destructor. So this is really convenient. Remember we talked about RAII in the past? So this is sort of RAII on this profile timer. So if I call profile timer T and give it a name, then this timer is going to start on its constructor. So the constructor of profile timer is going to call start. It's going to start the timing. Then some amount of code is going to run here, which takes some amount of time. And then the timer, once this function scope, once it leaves scope, this t will be destructed. And in the destructor of t, it's going to call stop. And so inside stop, it's going to log it, right? So just by calling this one line of code, we can now profile this entire function. And it will log it out to the JSON file, and we'll have all of that information. And what I could do in the exact same sort of way is not only profile a function, but any block of code, right? So anywhere I have a block of code that I want to profile, I construct the profile timer inside at that block of code at the top, give it a name. The timer is going to start when this is constructed. I do some stuff in the loop, and then when this block of code when it leaves scope, t is destructed, the destructor is called, and since stop is called in the destructor, the profiler is going to log it. So any scope of code that I want to profile, all I have to do is say profile timer t and give it a name. So here's how that works. Here's our profile timer class. It's going to include chrono. We have our profile result, so that's where the start and end times are going to be stored. And we're going to just record whether or not it's been stopped already. And we're going to record this starting time point as we did before. So our profile timer, it takes in a name, right? So this name is going to be whatever we want to appear in our output visualization. So we're going to store that name in the result, and we are going to store the starting time point as high resolution clock now. So that starts immediately. And then our profile timer destructor is going to call the stop function, which is on the next slide. So here again, when we construct this profile timer, it's going to start right away. It's going to record the starting point. And when the destructor goes off, it's going to stop and log it to the file. What does that stop function look like? Well, again, we're going to use namespace chrono. If the timer has stopped already, then don't do anything. So this prevents timers from being stopped twice and double logging. So I'm just doing that little error checking right here. Then it does the same thing that we did before, where we actually call high resolution clock now. We store the starting time and the end time in the result. And then we have, we record our thread ID, so I can actually get the thread ID as an integer in C++. And then what I do is I call profiler instance.writeProfile. And then that gets written out. And so here's what happens. Really simple. I just call my profiler, and on the constructor, it starts. On the destructor, it stops and logs. On the constructor, every iteration, it starts, and every iteration, it destructs and logs. Let's make it even more convenient. This is still a little bit annoying. We don't want to have to manually name the timers for every function that we call on it, right? So I don't want to name this myfunc every time. Maybe the function names will change. Then we have to go edit all the timers, right? What if, for development, of course I want to have this profiling on, but what if I want to turn off all of my profiling at once, or turn it on, right? So what we're going to do is we're going to create a macro. And macros can be very dangerous in C++, but they can also be very, very powerful. And this is going to be one of the cases where it's very, very powerful. It's going to do a bunch of stuff for us automatically. So here is our macro for profiling calls. Now I'm going to go through this line by line. I'm not going to explain all of the syntax of C++ macros, but a macro is essentially a find and replace text thing for the preprocessor. So I'm going to first define a macro called profiling. And if I'm going to say define profiling 1, that means that profiling has been defined. So enable profiling. So if I want to turn off all of my profiling, well, all of my profiling stuff is going to be defined within this if-def, which says if profiling is defined, do all this stuff, okay? But if I comment out this line of code so that profiling is no longer defined, then none of my profiling will actually happen. So this is why I'm doing it this way. So if we are profiling, I'm going to define a new macro called profile scope. And profile scope is going to have a name passed into it. And this name is whatever we pass into this macro. So if I say profile scope loop iteration, then in my visualization, loop iteration is going to be out there. Now, what this does is very clever, because I may have a bunch of timers that are being created, right? So this macro call is going to create a profile timer. Because I'm going to be creating possibly a bunch of simultaneous profilers, then I have to give them all different names, right? I have to give them different variable names. I can't call them all the same thing. And so what this line of code does is it says, create a profile timer, give the variable name timer, but then concatenate that name with the line of the file that this macro was called on. So if this macro was called on line 4 of your program, this will be profile timer, timer 4. If it was called on line 1026, then the variable name of this timer will be timer 1026. Right? So this is one of the cases where like the preprocessor gives us some really interesting tools. So this it ensures us that we have a unique profile timer name for the variable that we have to set up. So we have set up the profile timer. Now, profile scope is going to profile a particular block of code for us, a scope of code. However, what if I want to profile a function? Well, I'm going to define a macro based on another macro. So here, if I want to profile a function, there is actually a C++ preprocessor directive that can give me the name of the function that I'm currently calling. And that is __ function __. So profile function is a macro which calls profile scope with the name of the current function already in it. So profile function will not take any arguments because it will know the function that it's already in, and then it will call profile scope for that function. Isn't that cool? Like how we can actually tell the line of code that we're on and the function that we're on. This is pretty neat. So that's if profiling is enabled. Otherwise, if profiling is not enabled, then we just say, okay, these functions do nothing. And so if I comment out this line of code, define profiling, and then I recompile my program, that would be my program that I actually ship to the consumer. Because yes, this does add a certain amount of overhead. But what this enables me to do is that I can leave all of my profiling scope and profile function calls in my program and just undef this profiling thing, and then there will be zero overhead and none of the profiling will happen. So I can turn off or on all of the profiling in all of my functions. Oh my God, I had slides for this. I didn't have to explain that all at once. Okay, so macro ifdef. We define a macro called profiling. If profiling is defined, then the profiling macro is defined normally, causing the program to log to the JSON file. If profiling is not defined, then the macro is left blank by the preprocessor, turning off the profiler with zero overhead. Okay, so that wasn't so bad. But here's how we're going to use our profile timer macros. If I have a function that I want to profile now, all I do is call profile function. That's it. That's all I have to do. Isn't that cool? I don't know, man. If your mind isn't blown by that and you don't like programming, I don't know. I thought this was so cool the first time I saw it. And this was the main idea that came from the Cherno, right? Is the idea of doing this. Inside our function now, here is one thing where we would want to put, like, we want the option to be able to put a name in. If we do want to put a custom name in, so we wouldn't want to call profile function here because it would look like my function was called 10 times, right? So Here, we would call profile scope loop iteration because it's a loop iteration. So that's what we want. So here's an example. Like this is exactly what outputted this. So I have my function. That function is going to be called. I call profile function. Now I sleep for 1 second, which just eats up 1 second of time. Here, what I'm going to do is I'm going to do the following thing 10 times in a loop. I'm going to profile scope loop iteration, and then I'm just going to sleep for 100 milliseconds. So if I just do this in my code, and I run my code, what gets output to a JSON file is going to be this. If I drag this into Chrome tracing, this gets output, and it says, okay, look, it started at 0 milliseconds, it ran for a second, and then 10 loop iterations each ran for 100 milliseconds each. And I can just see that. I can just see it. It's really cool. Like, I don't know about you, but like this, I've used this in actual like production code. This is nice. All right. So now we're going to do a demo, and the code for the demo is on the code folder on the course website, which means that if you go to my website /courses/4300/code, it's there. I'll also put it on D2L. Okay, so I'll put this on D2L as well. All right, so let's use this thing. Let's do it. So don't save that. Now, here we go. Oh, geez, you can't see this at all. I have put all of that code that I just wrote into this profiler.hpp, and I put that on the website. So you can use this for your project if you want to, right? I've got profiling enabled here, and so I've got profile result right here. That's my profile result class. Here is the profiler class that I wrote. It writes out the profile. So this is the actual JSON syntax, which I'm not going to go over because you can just read that. This just outputs the result in the correct format. Then here's my profile timer code, right? I've got my start function and my stop function. It's a little bit more complicated. There's one extra thing that I did here. So this function is used to set and start the stop time. It adds 1 time unit if it's the same start time as the previous start time. So the Chrome tracing program has like a little bug in it where if 2 functions start on the exact same microsecond, then the visualization gets wonky. So what I do is I add 1 microsecond if it's the same time, and that's just to fix the Chrome tracing bug, okay? This is a 2 out of 10 on the janky fix scale, but it's worked for me in practice. So all of this is there, and you can use this in your project if you want to. So all I have to do to use that is include profiler. For example, if I want to profile my entire game engine, I can say include profiler.hpp, and then up here, I can say profile function. There we go. Now, let me make sure that this works. So let's run it. So it has to recompile, right? Okay, Mario, 1, 2, 3, 4, 5. Let's close the program. So my program ran for between 5 and 6 seconds, probably. So now let me quickly go out here to where this would have been outputted, because I didn't prepare that in advance. Okay, I've got a results.json file. Let's open that real quick. Here is my results.json file. Here's what got outputted. Function, duration, looks like it ran for about 7 seconds. The function's name was main. And here's the thread ID and all that other nonsense, all right? So let's open up Chrome. I will drag that results file into here, and look, main ran for 7.5 seconds. So I was bad at counting, all right? So I'm getting some nice comments out there in the chat. Thank you very much. I don't respond to all the nice comments, but I appreciate them. I try to leave my reading of the comments to just class questions. But just look at this. I profiled my main function, right? Isn't that pretty neat? Let's do that, but for more stuff now. So let's go around and add my profiler to more things. So really, let's go over to assets. All right, assets, load from file. Let's profile how long that took. So profile function. That's going to show me, oh, I didn't include profiling. So include profiler. There we go. Now I can use this. So load from file. That's going to show me how long it took me to do that. Add texture. Let's go down here. Let's profile that function. Add animation. Let's profile that function. Add font. Let's profile that function. Get font. No, I don't need get. I just want to see how long it takes to add stuff. All right. Now I've profiled all my assets. Loading. That's it. That was it. Pretty easy. So now let's go over to the game engine. The game engine constructor. Let's, screw it. Let's profile that. There we go. Oops, I need to include profiler. And oh, the game engine init, I want to profile that. Now, watch this. I want to profile the init function, but I also want to profile the loading of the file from assets. So how can I do that? Well, it turns out I can make a blank scope. And then I can say profile scope load assets. So this is how long it took to load the assets. Now, let's do another one. And I'm going to say here, profile scope. This is SFML window. So this will tell me how long the creation of the window took, right? So watch. Now I'll run this and we'll see what gets output. All right, let me run the game for a second or two. I don't want to run it too long because we're only really profiling the initialization stuff. But now my profile result file is 6 kilobytes. Wow. So let's drag it in. So now I've got the complete running of the program, right? You can see here my main function up on top. That took about 5 seconds. But if I zoom in, look at this. So I have my game engine constructor. It turns out that the initialization, let's go back and look at game engine. Game engine, well, the only thing that happened was init. So yeah, it makes sense that init took all of the time of the game engine. Within init, though, what was I profiling? I was profiling the loading of the assets and the creation of the SFML window. If I look in here, you can see, oh, wow. You may not think this. You'd think the loading of the assets took the longest, but it actually took longer to create the SFML window than to load the assets. Now, I have a really fast SSD, so if you have a spinning disk, this will probably not be the case. But look at this. Here is my assets load from file call. And then in here, we have assets add texture. Add texture, add texture, add texture. That's pretty neat, right? What if I want to know the loading of each texture? How long each texture took to load? Well, let's go back in here to our assets class. And when I'm adding texture, what I can actually do here is instead of calling profile function, let's call profile scope with path, right? So this now will tell us the texture that this was loading. And down here, I can do the same thing. I'm going to, but maybe here what I actually want to do is say like add texture. Let's see if I can add these things. Plus path, does that work? That might work. But it might not work because it's a macro. I don't know. Let's see if this works. Oh, okay, it compiled. Let's see what this actually looks like. Okay, we'll run it for a second. Boom. Now I have my profile result. Let's drag it over. Let's see what the assets do. Oh, look at this. So here's how long it took to load this texture. I could debug. Look, loading that explosion texture that was the biggest thing, right? So adding the texture of explosion. Oh, look, this one took a while. The big bush. Isn't this freaking cool? I don't know, man. I just get really excited about this kind of thing. In here, what was this? Add animation. The adding of the animation takes nothing, right? And the fonts, oh wow, the fonts took super long. So I could say, I want to know which font took so long to load. So I can do the same thing that I did up here for the textures, but I can do that for the font as well. So this is add font. So let's see the font culprit. Which font took so long to load? Okay, now that's it. I'm only looking at the initialization time. Now we'll drag in our new results. Then we'll come back over to here. We'll drill down into add fonts. Ah, wow, that's interesting. The tech font.ttf took the longest. If I look at my fonts file, that's because my tech font is actually 42 kilobytes, and these are much, much smaller. So that's amazing that I can drill down into it like this. And then know that, oh wow, the SFML window took that long? That's crazy. Come on, SFML window. Get your crap together. Now, let's keep going. Let's keep going with the profiling. Game engine. All right, what in game engine might I want to actually debug? Okay, so this is the user input. Let's look at the raw user input. So let's profile this function. All right. I don't want to do anything in there. Change scene. I don't think we want change scene. Okay, game engine update. Profile function. So each game engine update, we want to look at that. So I think that's what I want to do here. Now, if I go to my scene play, inside my scene play, I am going to include profiler. Let's see here. Scene play init. Let's profile that function. I want to know how long it takes me to initialize that. Maybe I want to know how long it took to load my level. Spawn player, hit block, spawn bullet, update, my update function. Ah, yes, here we go. My profile update in here, my entity manager update. I want to do that. I want to look at my entity manager, include profiler.h. Maybe I want to remove dead entities. No, add entity. All right, let's go back to scene play. I'm going to do my movement. I'm going to profile my movement. My lifespan. I'm just going to do all the systems. My collision system. My do action system. My drag and drop system. Why not? Animation system. Render system. And down here, if I really wanted to, I could profile the drawing of every individual entity. But let's not do that. Let's not do that. All right. So this is good enough for now. Let's look at how this works. All right. So all I had to do was add those things. Now I'm jumping around. I'm doing collisions. I got explosions playing. I'm firing some bullets, etc. Okay, that's enough. We'll go back. The results JSON file for that short run was almost a megabyte. Now let's have a look at it. Okay, this is where it starts to get cool. In here, what happened? Let's look at the trace of that program. So game engine update called game engine user input. What was this call in here? So the first user input was a little bit long. Game engine update, game engine update. This user input, this is probably where I was actually doing something with the user input. Now here, we finally get user input, scene play update. All right, so we finally get that. Scene play update. All right, so within our update, let's choose one in the middle so it's not the first one. Game engine update. All right, here we go. Game engine update. User input took a long time. Why is that? We'll debug that later. Scene play update. Here we go. Here are all my systems. So I can tell that the entity manager update took 0.4 of a second. My movement system took a little bit longer than the update for that. My lifespan took almost nothing. Oh, look, here's my collisions. My collision system took the longest amount of time. Here's my animation system, my drag and drop system, and then over here, here is my rendering system. So my whole update took longer than the render. But if you see this, look at this. Game engine update, which is the actual thing that runs at 60 FPS. Look at that. My game is only taking, my God, how long is this taking? This is like, I don't know, maybe a millisecond at most. And so I've got so much time here that I'm actually not doing anything. So let's see what is actually taking that amount of time. So if I come down here, scene play, well, in game engine, in the game engine update, the thing that is taking all the time, where is that? Okay, game engine update. All I did before was profile that, but if we come down here, I can say, all right, so profile scope. This will be the simulate, and so simulate is here. Then I'll put another scope here. This is going to be render. Here's my rendering. And then I'm just breaking this down so that I can display it for you. And then mwindow.display. This does the swapping of the buffers. So this is SFML waiting, essentially, right? This is SFML waiting to get 60 FPS for us. So let's run for a few seconds. Now we got a few seconds of data, and I load this back up, and here we go. So now inside each game engine update, look what I have. I have my user input, waiting for user input system. This is like the code, the user input inside game engine update. The simulating of each game frame, which involves scene, play, update, and then each of my systems. Then here, I've got the rendering, which is pretty much all just the scene, play, render. And then for the rest of this update, I'm just waiting for SFML. This is SFML waiting, right? So that's pretty neat that I can actually see that happening in this visualization now. And of course, if you have some sort of some other thing that you want to profile, for example, okay, why not? Let's put some let's drill down just a little bit harder, just to end the lecture with. So in my collisions, I want to see what's taking all the time in my collision system. So I'm going to go over to scene play. I'm going to go to my collision system. No, where's my collision system? Here we go. So this is player collisions. This is bullets and tiles. All right, so here we have, this is a scope of code that I want to profile. And so this is profile, scope, bullet, tile collisions. Down here, I have, this is player tile collisions. So I'm putting this scope in like this. Profile, scope, player, tile. And then do I have any other collisions? No, not really. All right, so the last thing I'll do here is just show you, we can see which of the bullet tile or player tile collisions. Here, I'm running around. This is player tile collisions. Now I'm going to fire some bullets, just that we have some data for the bullet tile collisions, and then I'm going to stop. Now I have my profile result over here. I'm going to take that, drag it in. Now you can see how deep this is getting, but we got to zoom in really far. Look at this. So initially, all of my collision time was player tile collisions because I didn't have any bullets on the screen, right? Then, if I zoom out and go to the end where I actually was firing bullets, let's get into one of these. Here we go. So now I can see that in my collision system, bullet tile collisions, because there were multiple bullets, are actually taking longer than the player tile collisions. So isn't that cool? It's pretty cool, I think. And if I go in to my profiler and I comment out this line of code and I recompile my program, there are errors. Oops, because I forgot this. So there's an error. Define profile function. There we go. Now it should work. Okay, so there's a slight error in the code. Now I come over here. I do all this stuff, and I exit, and my results JSON file is empty because nothing got output. Because it literally did nothing. So I defined this thing as nothing, and so literally what it does is it takes this and replaces it by nothing when I compile it like that. So there you go. That is visual profiling in C++. Easy enough for you to understand, implement, and actually use it in your final project if you want to. So if you have a slowdown somewhere, you'll be able to see that. Now just make sure you're in release mode because debug mode will probably make this run.